Inflection points are where we switch concavity. Remember, this is concave down when the second derivative is negative. And when the second derivative is positive, then we're concave up. So when it switches from concave down to concave up, then we've got an inflection point. So it's like critical points. You want to take the derivative. Actually, before I do that, let's distribute that x to the 1/3. X to the 1/3 times x makes x to the 4/3 because the powers add, right? When you multiply two things with the same base, the 1/3 plus 1 makes 4/3. And distributing it over here, we got 4x to the 1/3. I haven't done calculus yet, just algebra. So here's where we start calculus. I'm going to take the derivative. The 4/3 comes down, and then it gets reduced by 1. The 1/3 comes down, then it gets reduced by 1. There's our first derivative, but we want concavity, so we want the second derivative. So the 1/3 comes down, and then it gets reduced by 1. So 1/3 minus 1 makes negative 2/3. The negative 2/3 comes down, and then it gets reduced by 1. So negative 5/3. Okay, there's our second derivative. Now we want to set that equal to 0. So that's 4 over 9x to the 2/3 plus 8 over 9x to the 5/3. And then, just like with critical points, with potential inflection points, you set the second derivative equal to 0 and then list all the solutions or all the places where the derivative fails to exist. So at x equals 0, the second derivative fails to exist, right? So that's a potential inflection point that we'll want to test. And now let's try to solve. I want to get x out of the denominator. It's a 3, by the way. What can I do? I can multiply everything by x to the 5/3. That way I cancel out this 5/3 on bottom, and if you multiply x to the 5/3 to keep it balanced, you're just going to get 0 over here. So we got 4x to the 5/3 over 9x to the 2/3 plus, and I multiplied by 5/3 to make these cancel out, so plus 8/9. And then if you simplify over here, x to the 5/3 divided by x to the 2/3, the power subtract to make x to the first. So this is 4/9 x plus 8/9. 5/3 minus 2/3 makes 3/3. In other words, just x to the first power, positive power, so it stays up. And then if you solve that equation, subtract that 8/9 from both sides. Multiply both sides by 9. Then divide both sides by 4. So we got another potential inflection point at x equals negative 2. So what you'll want to do is sketch out a number line for yourself. Mark x equals 0, mark x equals negative 2, and then test points to the left and to the right of each of those. I'm going to want at least 3 points altogether. So let's try plugging in negative 3 into the second derivative to see whether it's concave up or concave down here. And so if I try to plug negative 3 into the second derivative, I've got fractional exponents that are messing with me. So a way to do that without a calculator is to rewrite them so that you have at least an integer for one of the exponents. Okay, I'll show you what I mean. Like this 4 over 9 x to the 2/3, that's the same thing as, let's see, the cubed root of x over x. Because remember, the cubed root means a 1/3 power, right? So if you got a 1/3 power and then x to the first power, they subtract to make x to the negative 2/3, which is what we had originally. So this is the same thing as this term. We'll do the same thing over here. We got x to the 5/3 in the bottom. So I'm going to put, look, it's 1/3 away from being x squared. So I just have to balance that out by putting the square root of x up here. Oh, wait, sorry, third root. So the third root of x up here. Okay, so now that we have integers and we got plain old radicals that we do understand, negative third is possible for odd radicals. I'm trying to think of how to say that. When the number of the radical is odd, like when it's not x squared, but when it's the cubed root of x or the fifth root of x or the seventh root of x, it's a negative result. I don't know exactly what number it is with a calculator, but I know this is going to be a negative number here. So if I plug in -3, I know this is going to be a negative, and I know this is going to be a negative, and a negative divided by a negative makes a positive. Uh-oh, that kind of messes up over here. Because this is going to be negative. No, we do have to figure out what that is. So let's take out our calculator. We got, I can just do the cubed root of 3 and then put a negative sign. So the numerator is -5.76 blah, blah, blah. That's the numerator. And then the denominator, I'm plugging in -3, so 9 times -3 makes -27. Okay, that's the first fraction when I plug in -3. And then with the second fraction, if I plug in that, I'm going to get the same thing. Oh, shoot, I lost it though. So the cubed root of 3 times 8 this time. The numerator on that second fraction is this when I plug in -3. It's positive this time. The denominator, -3 squared is 9. 9 times 9 is 81. Okay, we're really just interested in whether this is negative or positive. And actually, no, we don't have enough information to stop yet because they're still too close. That's what the first fraction is, positive. And then the second fraction, this. Oh, this is supposed to be negative, though. I forgot that. I'm very sorry. This is negative, right? The cubed root of -3 is a negative result. So that should be negative there. I messed that part up. So this is the first fraction. Hope I got that right. 11.53. That's negative. We'll add that to the first fraction's result. We got a positive number. Okay, so all that work, we found out that this is a positive number. So we found all potential inflection points. That means that everywhere to the left of -2 is going to be positive, assuming I plugged in that number correctly. Okay, we'll make our lives easier in this one, because if you plug in -1, we won't need as much calculator work. So we're plugging -1 into the derivative, the second derivative, I should say. So the cubed root of -1 is negative. So this is a -4 over 9 times -1, so that's -4 over -9. And then the cubed root of -1 is -1, so this is a -8 over 9. So this negative divided by negative makes a positive, so we got 4/9 plus -8/9. That's a negative number. Okay, that's a -4/9. So it's negative between our two potential inflection points. Okay. And then something to the right, if we plug in 1 into the second derivative, we can just use this one. If you plug in 1, you get 4/9 for the first fraction. You got 8/9 for the second fraction. So if you plug in 1, you get positive numbers. Okay. So what we just found out is that -2 and 0 are both inflection points. They're places where it switches direction. Okay. So -2 and 0 are indeed inflection points because the second derivative switches directions. It's concave up, and then it goes concave down, then it goes concave up. Okay, the other way to confirm this is to graph this in a graphing calculator. And I guess it's harder to see because you really got to understand concavity. But you should see that it's concave up before you get to -2. Then it's concave down to the right of -2 in between 0. Then it's concave up from 0 on. And they said points in the textbook. So these are the x-coordinates. You just need to plug them into the original equation to find the y-coordinates, right? So -2, comma, the y-coordinate by plugging it in. That's an inflection point. And plug in 0. That one's 0, right?